Okay, great. So we're into talking about classical Greece at the moment. And so we're beginning to see, and we'll continue to see, and this is a really important thing, is like how central geometry was to their math. And we could kind of ask the question, why would that be so? Well, last week there was that section on Pythagoras. So the Pythagoreans are the ones who are usually credited with the discovery of incommensurable quantities, or as we would say, the existence of numbers that are irrational. And this kind of freaked them out a little bit. So all of a sudden, their concept of number was what we would think of as rational numbers. So to them, rational numbers kind of make logical sense. That is what a number is. And all of a sudden, you've got a length which is not a rational number. So the problem is that a number at all? I mean, it's a length, so we can measure it, can't we? So how can it not be a number? So this is kind of what freaked them out. And is anyone here doing the book on Eudoxus, the Eudoxian solution? Or is that someone in the audience? Okay. Along came a mathematician called Eudoxus, and he solved that problem. And basically, he came up with a way of dealing with numbers, which when you look at it, just looks, what? It kind of looks, it's very subtle, and it's actually very similar to how in the 19th century, when there was again, this kind of demand for logical rigor, it's how Dedekind defined the real numbers. So has anyone seen Dedekind cuts? So it turns out the Eudoxian solution is basically the same as Dedekind cuts. And so this just put numbers on a solid footing, and that's how they were able to deal with irrational numbers. And we'll get to that later. Anyway, the whole point is this geometry sort of gave them this way of doing kind of math rigorously. And so, for example, we've seen that the Babylonians could handle quadratic equations. So they'd have some sort of recipe where, they would solve problems like, remember there's that one about the igum and the igubum, or whatever. So you're given a difference and a product, or you're given a sum and a product. We would just turn it into a quadratic equation, use the quadratic formula, and that's how we solve it. The Babylonians came up with a recipe which is exactly the same as the quadratic formula. It's actually a little bit more because they only allowed positive numbers, right? So for them, there wasn't one quadratic equation, like we have ax squared plus bx plus c equals 0. They had, x squared plus ax equals b, and ax plus b equals ax, depending upon whether a or b were positive numbers, where on the equation it was. So if you think about it, that gives more than one equation, okay? And so when the Greeks came along, they knew how to solve quadratic equations. They got this from the Babylonians, so it's well known that this kind of knowledge went from Mesopotamia into the Mediterranean region. So the Greeks knew how to solve quadratic equations, but after freaking out about irrational numbers, they had to say, yes, this recipe works. And Brett, in your book 2, you had a look, right? So I think it's proposition 5 and 6 are the ones that basically show that the quadratic formula works. Even though they don't sort of say it, you can look at it and you can interpret it as showing that the quadratic formula works. Okay, and so this is kind of how they did geometry. And so the Pythagoreans had all these ways of doing algebra, and then Euclid wrote about it and sort of proving it. But let's have a look at how they would do algebra. So let's have a look at the problem of application. The Greek word for that is paraboletai. I hope I'm pronouncing that correct. Now I'm really confused because, so para, right, is a Greek, nice Greek, is it a prefix? Right? What does para mean? Like in one sense, it means like put together. And so we have like parallel, which is like 2 lines together. We have, what's another para word? Parabola, we'll see that in a moment why that's the case. But then para also means beyond. So we have words like paradox, which means like beyond. Dox is something like idea or reason or something like that. So I'm always confused about how para can mean both alongside and beyond. So if someone can solve that mystery for me, I'd love to know. Anyway, this is called paraboletai, so which we translate as application. It actually means put alongside. And so here is the problem. You're given a segment of length A, and you've got an area of area capital A, and then at one end of the segment you've got a line. Now I've done it here as a right angle, but it actually doesn't have to be a right angle. It can be like at an angle like this. And the thing to do then is to construct a parallelogram of base A, this being one side of it, and the whole thing is area A. Okay. And of course, when it's a right angle, this is just the problem of solving big A divided by little a, because then that's going to be your height x. And so this isn't really algebra, it's just arithmetic, right? It's just division. And of course, it doesn't matter if it's not right angle. If it's at an angle, what's the area of a parallelogram? Well, it's still the base times the height. And so x would just be the height of the parallelogram. It wouldn't be the side of the parallelogram. Okay, so that's that. Now, what did they do? So they made the problems a little bit more fancier. So there's this problem of application with defect, which is they called ellipsis, which we know there's a word, right? Like when you do writing, ellipsis means like those 3 little dots, so there's a thing missing. So this is just a Greek word which just means missing. So this is application with defect. And you've got the same situation as before. You're given a segment, you're given a line that goes through the endpoint. I've done it here as a right angle. They actually posed as a parallelogram. It doesn't make any difference. And this is all the way that they did things, right? If they could do something in a more general way, they did. That's just the way they rolled. That was intellectually satisfying to them, even though they only ever really used it when it's at right angles with rectangles. But it holds for parallelograms. So the idea then is, given this, now you've got to put a parallelogram on, and here you're putting a parallelogram, or the rectangle with area A, and you have a defect. Now the defect isn't in the area, the defect is in the length. So don't get confused by that. So what it is the area of this whole thing then is A plus D. So it's an excess in area. Where the defect is in here, the defect is that you're not using all of A. Okay? And D has to be similar to some pre-given parallelogram. So, for example, you could say, I want it to be 3:2 or 2:1. Again, this is being more general. In reality, they would typically use a square. And what is this problem? Well, let's say x is the height of this rectangle here. So it's base by height. And so you've got x as the height, and the width here is A minus this. And if it's in proportion C to D, then this is D divided by C times x. So it's A minus D divided. So this is some pre-given number, minus x times x equals A. We recognize this as one of the quadratic formulas, right? And so what problem is this in reality? Well, it's finding two numbers. What haven't I used? M and N. So it's finding M and N such that M plus N is A, and M times N is big A. So it's a problem of finding numbers when you're given the sum and the product, which we know is just like a classic quadratic problem. Okay? And then we have application with excess. Anyone like to know guess what the Greek word for that is? What's something Greek meaning excessive, especially as a figure of speech? Exactly. Application with excess of hyperbolic. Okay, and so this is exactly the same thing. And again, the excess is in the length A here, not in the area, big A. In fact, it's kind of like a defective area, right? So this whole thing has to be A, and here's excess here. And so again, you want this whole thing to have area big A, and the base here is A, and then you add on, you have an excess to the length here, and again, this rectangle or parallelogram, whatever, has to be similar to one that's given. Okay, and so if you go ahead and figure it out, if x is the height, then the base then is A plus D over C times x multiplied by x. And this is just the classical problem of given a product and a difference, find the numbers. Okay, so yeah. So that's how it works. Okay. And so the thing you've all noticed is that the Greek terms here are highly suggestive. They're all mathematical objects that we all like: the hyperbola, the ellipse, and the parabola. And so let's talk about them. So this is conic sections. So someone is going to be talking. Who's going to be talking about? Anyone here going to be talking about conic sections? Nope. Okay. So we're going to be actually using them to solve problems. So it's good if we have. I'm going to give an introduction, and then someone's going to talk more about it. So, and it's not the easiest subject in the world, so it's good that we look at it multiple times. Okay, now the important thing is, don't think about conic sections in the way that you're being taught. Okay, so we all come from sort of a good analytic geometry background, right? Which was invented by Descartes and Fermat in the 1600s. You know, so you had to have Cartesian coordinates. Okay, that comes from Descartes, and you can make geometry. You can make these figures into kind of algebraic objects that you then deal with. So typically you think of a parabola as y equals x squared, and you think of an ellipse as, you know, x squared divided by a squared plus y squared divided by b squared equals 1. Or you might think of a hyperbola as x squared over a squared minus y squared over b squared equals 1. Actually, you probably think of a hyperbola as y equals 1 over x. That's okay. Okay. When the Greeks think about it, there is no equations, there's no x's, no y's. It's a rhetorical geometric construction. And so by rhetorical, I just mean it's all given just as a verbal description. Okay? And so what you do is you start with a circle, which you call a base, and a point outside the circle, and the lines running through the circumference of the circle and the vertex are called generators. And so these are these things here on the outside. You look at all the generators, and that's the outside of the cone. That's the boundary of the cone. Okay? And the line that goes from the vertex to the center of the cone, the center of the base, is called the axis of the cone. Okay, so notice that the cone is actually a double figure, right? Because it's a line through this point, through this, so the line also goes up here. So you get you get a double cone, one cone on top of the other. And the cone is a solid figure. So we typically think of a cone as just a surface, like you think of it like an ice cream cone. The cone is actually the solid object there. So typically, when it was first thought of, when you think of a cone, you think of it as a right cone in which the axis is perpendicular to the base. But again, they did the more general case. They thought of a generic cone where it doesn't have to be right, so the whole thing can be skewed at an angle, and everything still works the same. So you get the same results. So they started from the most general case, even though that it makes things more confusing. But we'll just think of right cones, just as it is. Okay. So what a conic section then is an intersection of the cone with a plane. So if you just think of it, we're just cutting the cone, and we're seeing what shapes we get. Okay, so again, this means that the conic sections are plane figures. They're filled in. So like, don't think about circles, think about discs. You know, so a parabola, you know, we think of a parabola as like this whole big curve. They thought of a parabola as, you know, that might be a parabola, that kind of thing like that. Okay? And so, for example, when they solve the problem of what is the area of a parabola, they don't think about the area underneath the curve, they think about finding this area right here, of that parabolic section. Okay, so it turns out that there are only 3 possible conic sections you can make, depending upon how you cut the cone. If you go through just one of the cones, you get an ellipse. And we're going to think of the circle as just a special case of an ellipse. If you go through both cones, like this, you get a hyperbola. And there's something in between a hyperbola and an ellipse. And that is if you make a cut parallel to a generator, it's just going to go through one cone, but it's sort of never going to come out the other side. So it's like the in-between case between the ellipse and the hyperbola. Okay. Now, what we are interested in are the properties of the conic sections, and these are called symptoms, another nice Greek word. Okay, and what happens when they use conic sections to solve problems, it's these symptoms that they're using to solve particular problems. Okay, so let's have a look at what those symptoms are. Oh, first we need some terminology. So here I have a conic section, and so I guess I've cut it off here, right? So we have the idea of a chord. So a chord is exactly the same thing as a chord of a circle, right? It's just, so here I've got a chord AB, it's just a line segment joining 2 points on the boundary of the conic section. Okay, so here is a theorem that's proven somewhere in the conics, that if you then take a chord and you look at all the chords parallel to it and join up the midpoints of these chords, you get a straight line. Sorry, I did this in paint and I can see that I actually didn't do a very good job of doing midpoint. These are all supposed to be joining up the midpoints. Okay? And that straight line is called a diameter. And the vertex of the diameter is where the diameter intersects with the boundary of the conic section. Okay. So you're also used to thinking of diameters as diameters of a circle, and it's obvious like that's true, right? Because if you take any chord, to look at all the lines parallel to that chord, join the midpoints, you get a diameter of the circle. And so for a circle, each diameter has 2 vertexes because it hits the boundary of the circle at 2 points. And it even turns out that the tangent at the vertex of the diameter is also parallel to all these lines here. Okay, and so this gives us some ordinates. So this length here, so half the chord is called an ordinate, and the length of the diameter up to that point is called an abscissa. Okay. So has anyone heard of ordinates and abscissas before? They're kind of like old-fashioned ways of talking about X and Y coordinates. So for example, for this chord here, YZ is the ordinate and XZ is the abscissa. And and then another theorem is if here the ordinate is not perpendicular to the diameter, right? When you do get a situation where the ordinate is perpendicular to the diameter, we call that diameter an axis, and it's kind of unique. For the parabola and the hyperbola, it turns out to be unique. For the circle, it's not unique, right? Because how many diameters does a circle have? It had all the diameters of a circle are axes, because all the diameters cut those chords perpendicularly. And how many axes does an ellipse have? Anyone remember their ellipses? We have an ellipse here. What do we call that ellipse? Oh, we have an axis there. What do we call that axis? Major axis? Everyone's forgotten their ellipses? Anyone want to guess what this is called? It's the minor axis, right? So an ellipse has two axes. Circles have infinite, but hyperbolas and parabolas only have one. Okay. And the vertex of an axis is called a vertex of the section. Okay, so an ellipse has four vertices. Circles, every point on the boundary is a vertex of the section. For a parabola, there's only one vertex, and for a hyperbola, there's two vertices of the section because it's got two branches. Okay. Let's talk about a parabola. Okay. So these are the symptoms of a parabola. The theorem: all diameters are parallel to the axis. So okay, so let's see. I'm a pretty crappy drawer of parabolas. So here is kind of like a parabola. And we all know where the axis of the parabola is. It's this one here. So here's the axis. And its chords are like this. That's supposed to be a horizontal line, right? And so quite obviously in this case here, the ordinates are x and the abscissa is y in just normal Cartesian terms. So that's how you would translate them. But this is also a diameter, and it's a diameter for, okay, I'll try. That's pathetic. It's supposed to be steeper. But if I'd done it correctly, this length would have been the same as this length. Okay? So the thing is, you can do algebra on this thing, nothing to do with like Cartesian coordinates. You can do all kinds of weird and funky different ways. People never do, but you can. Oh, sorry for that. Go back. Okay, now the most important theorem, and this is the one that is really used whenever you're doing anything with a parabola. For each diameter, there exists a parameter p. So remember what a parameter is. It's kind of like a constant, but it changes, right? So in each situation, it's constant, but you change the situation and it becomes a new constant. Okay, so like pi is a real constant. It never changes no matter what the situation. But parameter p, choose each diameter has its own constant, change the diameter and you change the constant. This parameter p is called the latus rectum. Don't know why we suddenly switched from Greek to Latin. So that means, I think, the upright side. So I'm sure there was a nice Greek term for it, but for some reason Latin is used, where we all know that a lot of Greek stuff came through Rome because Rome conquered Greece. And they respected Greek culture, so they picked up a lot of this. Okay, there exists a parameter p, the latus rectum, such that the rectangle of side p and abscissa equals the square on the ordinate. Okay, so if we let y be the abscissa, the area of the rectangle is p times y, and the square on the ordinate, if x is the ordinate, the square on the ordinate is just x squared. And so we get py equals x squared, and we all recognize this as a parabola that we know. Okay? And so that's good. And so it's this fact that you use whenever you solve a geometric problem with a parabola that you've got like this. And this kind of makes sense, right? Because the units match. Because this is an area and this is an area right there. Okay, and so in that problem that I showed you before, right, we had everything when we use the axis, we get py equals x squared. If we use that other diameter, the one parallel to it, we would have gotten a different parameter, but we would still get that same relation right there. Okay, and so this is exactly that problem of application that I showed you before, right? I give you an area, the area of the square on the ordinate. I give you a length, the latus rectum. You've got to find y. So this is a problem of application, of putting it next to each other. So this is that classic problem of application. Okay, so let's go on to the other ones. Hyperbola. What is its symptoms? Okay. So if you think about a hyperbola has got two branches, and there's a unique axis. So a hyperbola kind of looks like this. And so here's the axis. It's the one that sort of cuts them in half, right? Because then the ordinates are perpendicular to that axis. So this means that the hyperbola has a center. So if you look at the midpoint here, we've got a center of the section, and then all the diameters are all the possible lines through C. So this is another diameter of the hyperbola, and its sections are at an angle, so maybe they're kind of like that. They look sort of roughly equal, but they're not perpendicular. Okay. But we see that this center here, those things are always going to be of equal length. So it is a center. Okay. So let's get rid of. Oh, just start again. Okay. So I have my hyperbola, I have my center here, and so if I have a diameter, let's do a diameter here, like this. Okay. For each diameter, there's a parameter called the latus transversum, which is the distance between the two branches. I'm going to call that A. Okay. Theorem. For each latus transversum A, there is a latus rectum, P, such that the square on the ordinate equals the rectangle with sides the abscissa and the latus rectum with excess, a rectangle whose sides are in proportion P to A. So this is exactly this process that we call application with excess, which was in Greek hyperbolate. So this section was called the hyperbole, which we now call hyperbola. And so we get this picture that we see right here. Okay, so here we see CX is an abscissa, XY is an ordinate. So we have the square on the ordinate is there, and its square has to equal this rectangle here. Okay, so the rectangle has the abscissa as one side. Here is the transversum, and then we add on this little area right here, and that has to be P as is to A. So that means S, the area that we add, is to the abscissa as P as to A. So that means S, that area, that length we add, equals, what does that equal? It equals P on A times CX times the abscissa. And so we get the square on the ordinate, XY squared, equals P plus S times, because that's the length of this part of the rectangle, and CX, the abscissa, is this length here. So we get that, is that, but since S is P on A times CX, we get XY squared equals PCX plus P on A times CX squared. And does anyone recognize that as a hyperbola? It's not completely obvious. So what do we got to do? So if we let xy be x and cx be y, so we get py plus p on a times y squared. What's the algebraic thing we do with this? People remember the algebra? Complete the square. So we add some number squared. That means we have to subtract some number squared. All right, so we get x squared equals y plus r squared, maybe. I think so, because this is going to be a positive number, minus r squared, and so we get x squared minus y plus r squared equals r. Oh, no, I don't want to do it that way. I want to do it the other way, don't I? I want to do r squared equals y plus r squared minus x squared, and then I want to divide by r squared. And we get something that looks like more like a hyperbola. Okay, so we see in this process that, you know, when we have to make our, because we've got this excess here, we have to make our squares bigger than it would be for the parabola. So that's kind of like the excess. So we make it wider, so that makes it that hyperbolic state. And so it goes further away from each other. Then if we want to look at the symptoms of the ellipse, it's just the reverse. It's kind of the same, but with pluses instead of minuses. Okay. So with an ellipse, this is the problem with deficit now, and so the square on the ordinate has to equal this rectangle here, but we've taken things away. So that makes the square smaller, that's the deficit, and so that allows the arms to join together. Okay. And so you still have a latus rectum, and you still have a latus traversum. So for an ellipse, the latus traversum is just because an ellipse has a center, right? Where the two axes cross, you get a center. All diameters then are lines that go through the center. Only two of them are axes. This length here is the latus traversum. I forget what the latus rectum is, but you can kind of figure that out. And you get the same thing here, but since it's the defect, you replace the plus s by minus s. And so we get a minus sign here. And so when you do the thing and you complete the square, and now when you bring the two things together, you get like an x squared plus a y squared equals r squared. Well, not exactly y squared, right? Because there's p over a, so it distorts a little bit, and that distortion is exactly what you get in the ellipse. So that's that. And so to do these problems, then you just set up situations where you've got sort of lengths, and later on I'll show you applications where you actually use that. So I think that's as much as I want to do today. Any questions on any of this? Kind of made sense, hopefully. So the thing is, we can all relate it back to what you know about these. But notice it's important to note that the Greeks did not have the advantage that we do of having Cartesian coordinates. They did not think of these things in Cartesian coordinates at all. It's all simply a geometric process to us, to them. To us, we just write symbols down like I did before, right? And we just merely add and subtract quantities, and I do algebra, and that's how I show that it was like what it was. And in fact, when Descartes and Fermat came up with analytic geometry, their starting point was Apollonius. So the first place where analytic geometry was used was exactly this problem here, turning Apollonius into equations like we know. That was kind of step one in the program of analytic geometry. Okay, to be continued.